What if something out there decided to stay? Not by accident, not because it had to, but because it wanted to watch. Tonight, as you listen to this, somewhere between Mars and Jupiter, an object that should have left our solar system months ago is still here. It came from the void between stars, a place where no human eye has ever looked directly, and it entered our cosmic neighborhood at a speed that defies intuition. 200,000 kilometers per hour. Faster than anything we've ever built. Its name is 3I Atlas, the third confirmed interstellar visitor, and according to the data, it should have already vanished back into the dark. But it hasn't. I want you to do something before we go further. Wherever you are right now, whether it's day or night, look up. Imagine that something is looking back. Not with eyes, not with cameras we'd recognize, but with instruments we can't yet name, recording data we can't yet interpret. And then ask yourself, would we even know? The discovery happened quietly. On July 12, 2025, the Atlas Survey System, a network of robotic telescopes designed to scan the sky for asteroids, flagged an object moving against the flow, not in a typical elliptical orbit around the Sun, like most comets and asteroids, but in a hyperbolic trajectory, a path shaped like an open curve, not a closed loop. In other words, it wasn't bound to the Sun. It was passing through. The Minor Planet Center confirmed it 3 days later. Spectroscopic analysis followed. And within a week, the verdict was clear. This was not a local object. Its velocity, its composition, its trajectory, all pointed to an origin beyond our solar system. It was interstellar. The first interstellar object, 1I Oumuamua, had stunned astronomers in 2017. The second, 2I Borisov, arrived in 2019. Both had behaved according to expectation. They came, they passed, they left. No mystery beyond their existence. But 3I Atlas was different from the start. Its approach angle was nearly perfect. 5 degrees off the ecliptic plane, the flat disk where all the planets orbit. That's not impossible, but it's statistically unlikely. Most objects from interstellar space arrive from random angles, chaotic remnants of ancient stellar nurseries. This one came in almost aligned, like it knew where the planets were. Think of the solar system as a shallow pool of water. Most interstellar visitors dive in from above or below, cutting through at steep angles. But 3I Atlas entered the pool, almost horizontally, gliding just above the surface where all the worlds lie. The probability of this happening by chance is low. Not impossible, but low enough to make astronomers pause. And then there was the velocity. At 200,000 kilometers per hour, 3I Atlas was moving fast, but not too fast. Oumuamua had arrived at nearly twice that speed, screaming through the inner solar system in a matter of weeks before vanishing. 3I Atlas, by contrast, was taking its time. Its trajectory suggested a leisurely pass, a slow arc that would bring it close to the Sun, and then eventually carry it back out into the void. Except that's not what happened. By late August, something strange began to emerge in the orbital calculations. As astronomers refined their measurements, tracking the object night after night, correcting for gravitational perturbations from Jupiter and Saturn, the numbers kept shifting. Not dramatically, but enough to matter. The object was slowing down. Not much. Just a few hundred meters per second over the course of weeks. But in the vacuum of space, where nothing should slow you down unless you're hitting gas or dust, even a small deceleration is significant. And 3I Atlas wasn't passing through a dense nebula. It was in the relatively empty space of the outer solar system, where the density of particles is so low that friction is negligible. So what was slowing it down? The first explanation was simple: outgassing. When a comet approaches the Sun, its icy surface heats up and releases jets of gas and dust. Those jets act like tiny rocket engines, pushing the comet in unpredictable directions. It's called a non-gravitational force, and it's common. Oumuamua had shown similar behavior, though the details were never fully explained. But 3I Atlas didn't look like it was outgassing, at least not in the way comets usually do. There was no visible coma, no tail, no detectable cloud of particles streaming off its surface. Infrared observations from the Spitzer Space Telescope archived data from before the telescope was retired showed nothing. The object was cold, inert, almost invisible. And yet, the deceleration continued. By mid-September, a small group of researchers began circulating a hypothesis, not through official channels, not through peer-reviewed journals, but through private emails, conference backrooms, and late-night Zoom calls. The hypothesis was simple, almost absurd in its implications. What if the object was using the sun's gravity intentionally? What if it was aerobraking not through an atmosphere, but through the sun's gravitational well itself, slowing down just enough to remain captured in a long elliptical orbit instead of escaping back into interstellar space? It's called a gravity assist in reverse. Instead of slinging past a planet to gain speed, you use the gravitational pull to lose speed. NASA has done it with spacecraft. The Parker Solar Probe uses Venus this way, bleeding off velocity with each pass to drop closer to the sun. But for a natural object, a comet, a chunk of ice and rock to execute this maneuver would require a level of precision that defies randomness. You'd need to arrive at exactly the right angle, at exactly the right speed, at exactly the right moment. Unless, of course, you weren't random. Avi Loeb, the astrophysicist from Harvard who had proposed that Oumuamua might be an alien probe, was one of the first to say it out loud. In an interview published on September 18th, he described the possibility in characteristically blunt terms. If 3I Atlas remains in orbit around the Sun, we should consider the hypothesis that it was designed to do so. The reaction from the broader astronomical community was predictable. Skepticism, caution, a reminder that extraordinary claims require extraordinary evidence. And so far, all the evidence was circumstantial. Anomalous, yes, but not conclusive. Still, the question lingered. What if something out there had used the Sun not as a landmark, but as a destination? What if the solar system wasn't just a place to pass through, but a place to stay? And if so, why? We'll return to this anomaly later. But first, we need to understand what 3I Atlas actually is, or at least what it's supposed to be. When astronomers discover a new comet, the first thing they do is point a spectrograph at it. A spectrograph is essentially a prism attached to a telescope. It splits the light reflected off an object into its component, wavelengths its spectrum, and from that spectrum, you can determine what the object is made of. Every element, every molecule, leaves a unique fingerprint in the light. Hydrogen appears as a specific pattern of lines, oxygen, another, carbon dioxide, another still. For 3I Atlas, the first spectroscopic observations came from the Gemini North Telescope in Hawaii on July 18, 2025. The results were immediate and confusing. 95% carbon dioxide, 5% water. That's not how comets usually look. Most comets, especially those coming from the distant Oort cloud or the Kuiper belt, are dominated by water ice. H2O makes up the bulk of their mass, along with traces of methane, ammonia, and organic compounds. Carbon dioxide is present, but rarely as the dominant ingredient, and when it is, it's usually mixed with other volatiles in a chaotic, heterogeneous blend. But 3I Atlas was clean, almost too clean. The CO2 signature was sharp, consistent, and overwhelming. There was no methane, no ammonia, no complex organic molecules, just carbon dioxide and a trace amount of water, as if someone had filtered out everything else. One astronomer, speaking anonymously to a science journalist in early August, described it as unnervingly pure. The simplest explanation was that 3I Atlas had formed in a different kind of environment than our local comets. Perhaps it came from a star system where carbon dioxide ice was more common, where the protoplanetary disk had a different chemical makeup. Interstellar space is vast. There's no reason to assume all comets look the same. But even accounting for that, the purity was strange. Think of it this way. Imagine finding a stone on a beach that's made of 95% quartz and nothing else. No sand, no shell fragments, no salt residue, just quartz. It's possible. But you'd wonder how it got that way. What process refined it so thoroughly? For 3I Atlas, no such process was obvious. And then there was the size. Early estimates, based on the object's brightness and albedo, the amount of sunlight it reflected suggested a diameter of roughly 2 to 3 kilometers. That's Manhattan-sized, not enormous by comet standards, but not small either. Oumuamua had been far smaller, maybe a few hundred meters across. 2I Borisov had been closer in size, but still on the lower end. 3I Atlas was big enough to matter, big enough to carry instruments, big enough to house propulsion systems, big enough to be something more than a passive chunk of ice drifting through space. But size alone proves nothing. What made astronomers uneasy was the albedo itself. The object was dark, not pitch black, but darker than most comets. Its surface reflected only about 4% of the sunlight that hit it, which suggested either a thick layer of organic carbon common in comets or something else, something less reflective, less natural. One researcher compared it to charcoal, another to graphite. A third suggested it might be covered in a layer of silicate dust, baked and compressed over millions of years of exposure to cosmic rays. All plausible, all insufficient. By late August, a second round of observations began. This time, the European Southern Observatory's Very Large Telescope in Chile, one of the most powerful ground-based instruments on Earth, turned its attention to 3I Atlas. The goal was to capture high-resolution images to see if there were any structural features visible on the surface. There weren't. The object remained a point of light. No coma, no jets, no visible activity. Just a dark, silent speck moving slowly across the sky. But the VLT data did reveal something else. Rotation. 3I Atlas was spinning, slowly, once every 11 hours. That's not unusual. Most asteroids and comets rotate, but the rotation was remarkably stable. No wobble, no precession, just a clean, regular spin, as if the object were perfectly balanced. Again, possible, but unusual. Think of a spinning top. If it's smooth and symmetrical, it spins cleanly. If it's lumpy or uneven, it wobbles. Natural objects, comets, asteroids are almost always lumpy. They're rubble piles, held together by weak gravity and frozen volatiles. They tumble more than they spin. 3I Atlas spun like an engineered object. Not proof, but suggestive. And then, in early September, something even stranger appeared in the data. A team of radio astronomers at the Very Large Array in New Mexico had been monitoring 3I Atlas at the 1420 MHz frequency, the so-called hydrogen line, a wavelength that's often used in SETI searches, because it's a natural frequency that any technological civilization might use for communication. They detected nothing, no signals, no patterns, just cosmic noise. But what they did detect was an absence. The object was radio quiet, completely silent. Not even the faint electromagnetic hiss that most objects emit when they interact with the solar wind. It was as if 3I Atlas were wrapped in something that absorbed radio waves instead of reflecting them. Again, possibly natural, possibly a quirk of the object's composition, possibly nothing. But astronomers were starting to accumulate a list of anomalies. Individually, each one could be explained. Collectively, they formed a pattern, and patterns demand explanations. It shouldn't be possible for an interstellar object to arrive aligned with the ecliptic, composed almost entirely of CO2, spinning with perfect stability and absorbing radio waves, not all at once. Not unless there was something about its structure, something about its design that we hadn't yet recognized, unless we've misunderstood what a comet really is. In October, the speculation became formal. On October 3, 2025, a preprint paper appeared on the Archive server, a repository for research that hasn't yet been peer-reviewed. The title was cautious: Non-Gravitational Perturbations and Orbital Capture Scenarios for Interstellar Object 3I Atlas. The author list was small: 3 researchers, 2 from minor universities, 1 independent. But the content was anything but cautious. The paper proposed that 3I Atlas might not be a single object. Instead, it could be a carrier, a mothership designed to release smaller probes once it reached a stable position within the solar system. The idea wasn't entirely new. It had been floated before in the context of Oumuamua and dismissed for lack of evidence. But with 3I Atlas, the authors argued, the evidence was mounting. The logic went like this: if the object was intentionally decelerating, it needed a mechanism. Outgassing alone couldn't explain the observed trajectory changes because there was no visible outgassing. That left 2 options. Either the object had an internal propulsion system unlikely to be detectable from Earth, or it was shedding mass in a controlled way. Shedding mass, like a dandelion releasing seeds. The metaphor was deliberate. A dandelion doesn't move. It stays rooted in the ground, but when the wind blows, it releases hundreds of tiny seeds, each one carried to a new location. Some land nearby, some travel kilometers. Each seed is a potential new dandelion, waiting for the right conditions to grow. Now imagine that on a cosmic scale. A mothership arrives in a star system, not to land, not to communicate, but to distribute. It releases smaller probes, each one autonomous, each one equipped with its own power source and instruments, and those probes spread out, drifting into different regions of the system. Some might head toward the inner planets, others toward the outer gas giants. A few might even remain in orbit around the sun itself, waiting, watching, recording. And the mothership? It stays behind. A silent anchor, a relay point, or perhaps just a discarded shell, its purpose fulfilled. The paper didn't claim this was happening. It only claimed it was possible. But the possibility was enough. Within days, the preprint had been downloaded. Thousands of times. Science journalists picked it up. Reddit threads exploded. And somewhere in the background, quietly, a few researchers at NASA and ESA began running simulations. What would it take to detect a small probe, say, 10 meters across, released from a larger object millions of kilometers away? Could our current instruments resolve it? Could we track it? The answer was, maybe, if we knew where to look. But we didn't. The problem with the mothership hypothesis is that it requires surveillance, constant high-resolution surveillance. You'd need to watch 3I Atlas continuously, with multiple telescopes, from multiple angles, looking for any sign of ejected material. And even then, if the probe were small enough, if it were designed to be stealthy, it might slip through unnoticed. Space is dark, objects are small, and our instruments, powerful as they are, can only see what reflects light. Still, the hypothesis gained traction for a simple reason. It explained the anomalies. It explained the deceleration. If the object was releasing mass-shedding probes that would create a recoil effect, slowing it down incrementally. It explained the lack of outgassing. If the probes were ejected cold, without the heat-driven jets of a comet, there'd be no visible coma. It even explained the radio silence. If the object were designed to be inconspicuous, it would make sense to minimize electromagnetic emissions. But it also raised uncomfortable questions. If 3I Atlas was a mothership, where were the probes going? Were they heading toward Earth, toward Mars? Were they already here, drifting in orbit around our planet? Too small to detect, too quiet to notice. And if so, what were they looking for? One astrophysicist, in a blog post that quickly went viral, framed it this way. We spend billions searching for signs of extraterrestrial intelligence. We point telescopes at distant stars, listening for radio signals, looking for megastructures. But what if intelligence doesn't announce itself? What if it just watches? He called it the silent observer hypothesis. The idea is simple. A sufficiently advanced civilization wouldn't need to communicate with us. It wouldn't need to make contact, to send messages, to reveal itself. It would only need to observe, to gather data, to understand who we are, what we're capable of, and whether we pose a threat or an opportunity. And the best way to observe is to remain unseen. Think of it like wildlife photography. You don't walk up to a lion and introduce yourself. You hide. You use a telephoto lens. You watch from a distance, silent and still, until the animal behaves naturally. Only then do you understand its true nature. Maybe that's what 3I Atlas is. A telephoto lens. A camera pointed at Earth, waiting for us to reveal ourselves. Or maybe it's simpler than that. Maybe it's just a comet, a chunk of carbon dioxide ice from some distant, oxygen-poor star system, following the blind mechanics of gravity. But if that's true, why does the data keep insisting otherwise? We'll return to this anomaly later, but first we need to talk about what happens on October 29th. October 29th, 2025 is the day 3I Atlas reaches perihelion. Perihelion is the closest point in an orbit to the Sun. For Earth, it happens every January, and we barely notice our distance from the Sun changes by only a few %. But for comets, Perihelion is everything. It's the moment of maximum heat, maximum stress, maximum transformation. It's when the ice sublimates, when the tail forms, when the object becomes visible to the naked eye. For 3I Atlas, perihelion means something else: invisibility. At perihelion, the object will pass within 0.3 astronomical units of the Sun, about 45 million kilometers. That's closer than Mercury. And from Earth's perspective, it will be almost directly behind the Sun, lost in the glare. We won't be able to see it. Not with ground-based telescopes, not with Hubble, not even with the James Webb Space Telescope, which is designed to look deep into space, not directly at the Sun. For roughly 3 weeks from mid-October to early November, 3I Atlas will vanish into what astronomers call the solar exclusion zone. It's a blind spot, a gap in our surveillance, and that's when the object is most likely to change. Think of it this way. Imagine you're watching someone walk through a crowded room. You keep your eyes on them the whole time, but then they step behind a pillar. For a few seconds you can't see them, and when they emerge on the other side, they're wearing a different coat. Did they change while hidden, or were you just not paying attention? For 3I Atlas, the question is literal. If the object is natural, just a comet perihelion should be uneventful. It might brighten slightly as sunlight heats its surface. It might release a small amount of gas, but it won't fundamentally change. When it emerges from behind the Sun in early November, it should look more or less the same as it did going in. But if it's something else, if it's artificial, if it's controlled, if it's executing a maneuver, perihelion is the perfect moment to act. Hidden from view, shielded by the Sun's glare, it could alter its trajectory, release probes, or reconfigure itself in ways we wouldn't detect until it was too late. Too late for what? That's the question no one wants to ask out loud. By mid-October, a quiet sense of urgency had settled over the small community of astronomers tracking 3I Atlas. Not panic, not alarm, but a low hum of unease, the kind that comes from knowing you're about to lose sight of something important. Several research teams submitted emergency observation requests to NASA and ESA, asking for time on solar observatories spacecraft like the Solar Dynamics Observatory and the Parker Solar Probe, which are designed to stare directly at the Sun and might, just might, catch a glimpse of 3I Atlas as it passes through the exclusion zone. The requests were approved, but no one was optimistic. The Sun is bright, unimaginably bright. Its corona extends millions of kilometers into space, a superheated plasma that drowns out everything nearby. Detecting a small, dark object moving through that glare is like trying to spot a mosquito flying past a searchlight. Possible in theory, nearly impossible in practice. And so for 3 weeks, 3I Atlas would be invisible, but not silent. Because there's one place where the Sun's glare doesn't matter: radio astronomy. Radio waves pass through the Sun's corona relatively unaffected, and while 3I Atlas had been radio quiet during its approach, there was a chance, however small, that it might emit something during perihelion. A burst of electromagnetic noise, a faint signal, anything. Starting on October 20th, the Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, and the SETI Institute's Allen Telescope Array in California all turned their attention toward the projected path of 3I Atlas. They listened at multiple frequencies: the hydrogen line at 1420 MHz, the water line at 22 GHz, and several others. For 9 days, they heard nothing. And then, on October 29th, the exact day of perihelion, a brief anomaly appeared in the data from the VLA. Not a signal, not a structured transmission, but a momentary spike in radio noise lasting less than 3 seconds, centered around 1420 MHz. It was faint, barely above the background, and it could have been anything. A glitch in the receiver, interference from a satellite, a random fluctuation in the Sun's own radio emissions. But it was there. The team analyzed the spike for hours. They cross-referenced it with data from other observatories. They checked for terrestrial sources, aircraft, military radar, cell towers. They found nothing conclusive. The spike remained unexplained. And by the time they finished their analysis, 3I Atlas had already passed behind the Sun. Now, we wait. The object will emerge from the solar exclusion zone on November 8, 2025. When it does, every major telescope on Earth will be watching. Gemini, Keck, the Very Large Telescope, the Hubble Space Telescope. Even amateur astronomers with backyard setups will be pointing their lenses toward the expected coordinates. The question is simple: will it still be there? And if it is, will it look the same? Because if the object has changed, if its trajectory has shifted, if its brightness has increased, if new structures have appeared, then we'll know. We'll know that something happened during those 3 weeks, something we weren't supposed to see. And if it hasn't changed, if it emerges exactly as predicted, following the same orbit, spinning at the same rate, silent and dark and unremarkable, then maybe we'll breathe a sigh of relief, or maybe we'll wonder what we missed. On November 2nd, while 3i Atlas was still hidden behind the sun, something unexpected happened. A post appeared on an amateur astronomy forum. The user, someone with the handle Skywatcher47, claimed to have detected a repeating radio signal coming from the direction of 3i Atlas. The post included a spectrogram image, a frequency analysis, and a timestamp, October 31st, 11:34 p.m. UTC. The signal, according to the post, was a series of short pulses, each lasting approximately 0.8 seconds, separated by intervals of 3.2 seconds. The frequency was 1422 MHz, just above the hydrogen line. The post went viral within hours. Reddit threads exploded. Twitter lit up. Science YouTubers scrambled to analyze the spectrogram. And within a day, the story had been picked up by several major news outlets, framed with headlines like "Amateur Astronomer Detects Alien Signal from Interstellar Object" and "Is 3i Atlas Trying to Communicate?" The reaction from the professional astronomical community was swift and unequivocal. Skepticism. First, the claim was extraordinary. Extraordinary claims require extraordinary evidence. A single amateur observation, posted anonymously on a forum, doesn't meet that standard. Second, the spectrogram, while superficially convincing, showed several red flags. The signal appeared too clean, too regular, too much like what someone expects an alien signal to look like, rather than what real radio data usually looks like. Third, and most damning, no other observatory had detected anything. The VLA, which had been monitoring the region continuously, reported nothing at 1422 MHz on October 31st. Neither did Arecibo. Neither did the Allen Telescope Array. If the signal had been real, at least one of these instruments should have picked it up. By November 4th, the consensus among experts was clear. The signal was either a hoax, a misidentification of terrestrial interference, or a genuine mistake by someone who didn't fully understand their equipment. Case closed, or so it seemed. Because on November 5th, another post appeared, this time from a different user, in a different forum, and this time, the claim was slightly different. The second user, RadioHawk89, didn't claim to have detected a signal. Instead, they reported an absence. They'd been monitoring the hydrogen line for weeks, and on the night of October 31st, there had been a brief dropout, a momentary silence, as if something had blocked the signal. The dropout lasted about 12 seconds, and it occurred at exactly the same time as the alleged signal reported by Skywatcher47. Now things were getting strange. A signal and a dropout, both reported independently, both occurring at the same time. Coincidence, coordination, or something else? The professional community remained skeptical, but a few researchers quietly began to take notice. One of them was a radio astronomer at Jodrell Bank Observatory in the UK. She pulled the archived data from her own telescope for the night of October 31st and ran a detailed analysis. She found nothing at 1422 MHz, but at 1419 MHz, just below the hydrogen line, she found a faint, transient feature. Not a signal exactly, more like a ripple, a momentary distortion in the baseline noise. She didn't publish her findings. She didn't even write them up. But she sent an email to a colleague at the SETI Institute, describing what she'd seen and asking if anyone else had noticed anything similar. The colleague replied within hours, "We saw something too, different frequency, same time frame, we're not sure what it was." And that's where things stood on November 7th, 2025, one day, before 3i Atlas was scheduled to emerge from behind the sun. The amateur signal claims had been debunked. The professional observations remained ambiguous, and no one was willing to go on record saying they believed something unusual had happened. But privately, in email chains and Slack channels and late-night phone calls, a question was circulating. What if the signal wasn't meant for us? What if it was internal communication, a probe transmitting data back to the mothership, or vice versa? What if we weren't the intended audience, just accidental eavesdroppers? And if that were true, what would it mean that the transmission happened during perihelion, when the object was hidden from Earth's view? It would mean the object knew when we couldn't see it. It would mean the object was aware of us. And it would mean we were being watched by something that didn't want to be watched back. But none of this was proven. None of it was conclusive. And by November 8th, the entire debate became moot. Because that's the day 3I Atlas reappeared. On November 8, 2025 at 3:17 a.m., the Gemini North Telescope in Hawaii captured the first post-perihelion image of 3I Atlas. The object was there, exactly where the orbital calculations predicted it would be. No deviation, no surprise. It was still dark, still silent, still spinning at the same 11-hour rotation period, and it was alone. For those who had hoped or feared that the object might have changed during its passage behind the sun, the data was almost disappointing in its consistency. No visible probes, no structural alterations, no anomalous outgassing. Just a dark speck of light, moving slowly across the sky, precisely as expected. The relief was palpable. Within hours, several major news outlets ran stories with headlines like "Interstellar Comet Emerges Unchanged" and "3I Atlas Behaves Normally After Solar Flyby." The implication was clear. The speculation had been overblown. The object was natural. The mystery was over. But for a small group of researchers, those who had been tracking the object most closely, the data told a more complicated story. Yes, 3I Atlas had emerged at the expected location, but its velocity had changed. Not by much, just a few hundred meters per second, but enough to matter. The object was moving slower than it should have been. Orbital mechanics are precise. When a comet passes around the Sun, it accelerates due to gravity, gains speed at perihelion, and then slows down as it climbs back out of the gravitational well. The amount of acceleration and deceleration is entirely predictable, determined by the object's mass, velocity, and distance from the Sun. For 3I Atlas, the calculations had predicted a post-perihelion velocity of approximately 205,000 kilometers per hour. The measured velocity was 203,400 km/h, a difference of 1,612 km/h. That might not sound like much, but in space, small differences accumulate. Over weeks and months, a velocity discrepancy of 1,600 km/h translates into a positional error of millions of kilometers, and more importantly, it shouldn't exist unless the object lost mass, or gained drag, or used thrust. The first explanation, mass loss, was possible. If the object had shed material during perihelion, that would create a recoil effect, slowing it down. But there was no visible debris field, no trail of dust or gas, no evidence that anything had been ejected. The second explanation, drag, was implausible. The solar wind at 0.3 AU is thin enough that even a small object like 3I Atlas would experience negligible drag. Certainly not enough to account for a 1,600 km/h velocity change. That left the third explanation, thrust. On November 10th, a second paper appeared on the Archive server. This one was authored by a team from MIT and included a detailed analysis of the post-perihelion velocity anomaly. The conclusion was carefully worded. The observed deceleration is inconsistent with non-gravitational forces expected from a passive body. If natural processes cannot account for the velocity change, alternative explanations, including directed propulsion, should be considered. Directed propulsion. The paper didn't say alien spacecraft. It didn't need to. The implication was clear, and this time the broader astronomical community couldn't dismiss it outright. The data was solid, the analysis was rigorous, and the discrepancy was undeniable. Something had slowed 3I Atlas down, but that wasn't the only anomaly. On November 12th, Astronomers at the Keck Observatory in Hawaii reported a subtle change in the object's spectrum. The CO2 signature was still dominant, but now there was a faint trace of something else. Silicate dust, very faint, barely detectable, but present. Silicate dust is common on comets. It's the rocky component, the non-volatile material that doesn't sublimate. But 3I Atlas hadn't shown any silicate signature during its approach. The spectrum had been clean, just CO2 and water. So where had the dust come from? One possibility, the object had fractured during perihelion. The intense heat and gravitational stress might have cracked the surface, exposing fresh material underneath. If that material was richer in silicates, it would explain the new spectral feature. But if the object had fractured, there should be other signs. Changes in brightness, irregularities in the light curve, evidence of fragmentation. There were none. The object remained intact, stable, unchanged, except for the dust. And then on November 14th, the strangest detail emerged. A team of researchers analyzing high-resolution images from the Hubble Space Telescope noticed something odd. The object's brightness had increased, not dramatically, just a few percent. But the increase was asymmetric. One side of the object appeared slightly brighter than the other. It was as if something on the surface had been activated or exposed. The team ran simulations trying to model what could cause such an asymmetry. They considered surface roughness, variations in composition, shadowing effects from irregular topography. Nothing fit perfectly, but one model came close. A reflective patch, a small region on the object's surface, perhaps a few hundred meters across, that reflected sunlight more efficiently than the surrounding material, like a panel, or a mirror, or a sensor array. The data was suggestive, but not conclusive. And that's the problem with 3I Atlas. Every piece of evidence taken individually has a plausible natural explanation, but collectively they form a pattern that refuses to resolve into either pure coincidence or deliberate design. It's the ambiguity that's most unsettling, because if the object is natural, then we're witnessing an extraordinary convergence of unlikely events, and if it's artificial, then we're watching something that doesn't want to be recognized. Either way, the object is still here. And on November 15th, astronomers confirmed something that many had suspected but few had dared to say out loud. 3I Atlas was not leaving. Its trajectory, refined after days of post-perihelion observations, showed a clear elliptical orbit, not a hyperbolic escape path, not a flyby, an orbit. The object had been captured by the sun. Whether by chance or by design, 3I Atlas was now a permanent resident of the solar system. And the question everyone was asking, the question no one could answer, was simple. What happens next? To understand what it means for 3I Atlas to remain in orbit, you have to understand how orbital capture works. Imagine throwing a ball straight up into the air. If you throw it gently, it rises a short distance and falls back down. If you throw it harder, it rises higher before falling. But if you could throw it fast enough, about 11 kilometers per second on Earth, it would never fall back. It would escape into space. That critical speed is called escape velocity. For an object approaching the sun from interstellar space, the same principle applies in reverse. If the object is moving faster than the sun's escape velocity at any given distance, it will pass through the solar system and continue into the void. If it's moving slower, it gets captured into an orbit. The boundary between the two is razor thin. For 3I Atlas, the initial velocity measurements from July and August clearly indicated a hyperbolic trajectory and escape path. The object was moving fast enough to leave, but by early November, after the perihelion passage, the velocity had dropped just enough to shift the trajectory from hyperbolic to elliptical. The object was now bound to the sun. The new orbit, according to preliminary calculations, has a semi-major axis of approximately 150 AU 150 times the Earth-Sun distance. That places the aphelion, the farthest point in the orbit, somewhere beyond the Kuiper belt, in the outer reaches of the solar system. The orbital period is estimated at around 1,800 years. In other words, 3I Atlas will spend the next several centuries drifting outward, far from the sun, before eventually returning to the inner solar system in the year 3825. But there's a problem with that timeline. The problem is energy. When an object transitions from a hyperbolic to an elliptical trajectory, it has to lose energy. That energy has to go somewhere. In most cases, it's dissipated through gravitational interactions, close encounters with planets, resonance effects with Jupiter or Saturn, or tidal forces near the Sun. But 3I Atlas didn't have any close encounters. Its trajectory kept it far from the major planets, and tidal forces, while present, aren't strong enough at 0.3 AU to account for the observed energy loss. So where did the energy go? One possibility: it was radiated away. If the object's surface absorbed heat from the Sun and then re-emitted it asymmetrically, perhaps due to outgassing or thermal expansion, that could create a small but persistent thrust, like a slow-motion rocket engine. This is called the Yarkovsky effect, and it's well documented for small asteroids. But 3I Atlas showed no evidence of outgassing, no coma, no jets, no thermal plume. Another possibility: the energy was transferred to something else. If the object ejected mass during perihelion small probes, perhaps, or even just dust particles that would create a recoil effect, robbing the main body of momentum and slowing it down. But again, no debris field was detected. The third possibility is the one no one wants to say out loud, but everyone is thinking: the energy was converted intentionally, harvested, stored, used. If 3I Atlas is artificial, if it's equipped with propulsion, power generation, or even just passive control surfaces, it could have modulated its trajectory deliberately, not with a dramatic burn like a rocket, but with subtle, continuous adjustments, a slow bleed of velocity, spread out over weeks, invisible to our instruments. Think of it like sailing. A sailboat doesn't need an engine to change direction. It uses the wind. And if you're clever enough, you can use the sun's radiation pressure, the solar wind, even the magnetic fields that permeate space, to nudge your trajectory bit by bit. Advanced enough technology wouldn't look like propulsion. It would look like physics. And that's the nightmare scenario, because if 3I Atlas used the sun's own energy to capture itself into orbit, then it's not just visiting. It's staying, by design. But why? Why would an interstellar object, natural or artificial, want to stay in the solar system? One answer: observation. If the object is a probe sent by some distant civilization, its purpose might be simple: gather data. And the best way to gather data over long timescales is to establish a stable orbit. Not too close and you risk being damaged by heat or detected by the locals, but not too far either. You want to be near enough to watch, to measure, to record. An elliptical orbit with a 1 to 800 year period is perfect. You spend most of your time in the outer solar system, where it's cold and dark and safe. But every 2 millennia you swing back through the inner system, passing close to the planets, close to Earth, gathering fresh data before retreating again. It's patient, it's efficient, and it's exactly what you'd do if you were building a long-term surveillance network. But there's another possibility. What if 3I Atlas isn't here to observe us? What if it's here to observe something else? The sun. Stars are fascinating objects. They're massive nuclear furnaces, burning hydrogen into helium, generating light and heat and magnetic fields that shape entire planetary systems. And they're dynamic. They flare, they pulse, they evolve. If you're an advanced civilization trying to understand stellar physics, you don't study stars from light years away. You go there, you get close, you measure. And if you're really advanced, you don't send a single probe. You send many. You seed multiple star systems with monitoring stations, each one collecting data, each one transmitting back to some central archive. 3I Atlas might not care about us at all. We might be irrelevant, just another species of semi-intelligent apes orbiting an unremarkable G-type star. The sun, on the other hand. The sun is worth studying, but there's a third possibility, one that's even stranger. What if 3I Atlas is here because it's waiting? Waiting for what? For us to notice, for us to respond, for us to prove we're worth talking. 2. Think of it as a test, a cosmic waiting room. The probe arrives, parks itself in a conspicuous orbit, and waits to see if the locals are advanced enough to recognize it. If we are, if we send a mission, if we attempt communication, if we demonstrate curiosity and capability, then maybe the probe reveals itself. Maybe it responds. But if we're not, if we ignore it, if we dismiss it as a comet, if we lack the technology or the will to investigate, then the probe simply waits, silent, patient, for centuries. And when it finally swings back through the inner solar system, 1,800 years from now, it checks again. Are the locals still here? Have they advanced? Are they ready? If not, it waits another cycle, and another, until either we evolve into something worth noticing or we go extinct. It's a chilling thought, but it fits the data, because the one thing 3i Atlas has done consistently since its discovery is refuse to reveal itself completely. It shows just enough to be anomalous, just enough to raise questions, but never enough to confirm or deny. It's keeping us guessing, and maybe that's intentional. Maybe the ambiguity is the test. On November 18, 2025, NASA's Juno spacecraft, currently in orbit around Jupiter, detected something unusual. Juno wasn't looking for 3i Atlas. It wasn't even pointed in the right direction. Its mission is to study Jupiter's atmosphere, magnetic field, and interior structure. But Juno carries a suite of instruments, including a high-sensitivity magnetometer and a plasma detector, both of which continuously monitor the space environment around the spacecraft. And on November 18th, those instruments recorded a brief disturbance. It lasted less than 2 minutes. A sudden spike in charged particle flux, followed by a rapid drop. The magnetometer showed a corresponding fluctuation in the local magnetic field, small but measurable. The Juno science team analyzed the data for several days. They ruled out solar activity there. Had been no coronal mass ejections or solar flares around that time. They ruled out Jupiter itself. The disturbance occurred on the day side of the planet, far from the intense radiation belts. That left only one plausible explanation. Something had passed nearby. Something that briefly altered the local space environment before moving on. But there was nothing scheduled to be near Jupiter on November 18th. No asteroids, no comets, no spacecraft. Except possibly something small, something untracked. The Juno team ran a trajectory backtrack, trying to determine where the disturbance might have originated. The calculations were rough. Magnetometer data alone isn't enough to pinpoint a source, but the best-fit solution placed the origin somewhere in the direction of the inner solar system, the direction where 3i Atlas had been 3 weeks earlier. The timing was suggestive. If 3i Atlas had released probes during perihelion's small, fast-moving objects, each on its own trajectory, some of them might have reached Jupiter's orbit by mid-November, and if one of those probes passed close enough to Juno, it might have created exactly the kind of disturbance the instruments recorded. But this is speculation. The data is ambiguous, and the Juno team, in their official report released on November 25th, was careful to avoid jumping to conclusions. They noted the anomaly, described the possible trajectories, and left it at that. No mention of 3i Atlas, no mention of probes. But the report was public, and within hours, independent researchers had made the connection. A Reddit thread titled, "Did Juno just detect a probe from 3i Atlas?" gained thousands of upvotes. Science bloggers dissected the magnetometer data, and once again, the speculation machine spun up. Was it real? Was it coincidence? Or was it confirmation? We don't know, but there's a detail in the Juno data that hasn't received much attention. A detail that, if real, changes everything. The disturbance wasn't random. The magnetometer spike showed a pattern, a repeating structure, not quite periodic, more like a modulation, as if the source of the disturbance were pulsing or oscillating at a specific frequency. The frequency was 0.47 Hz, one pulse every 2.1 seconds. Now 0.47 Hz is not a natural frequency. There's nothing in plasma physics or magnetospheric dynamics that would produce such a clean, regular oscillation. It's not impossible. Nature is full of surprises, but it's unlikely. And it's eerily similar to the pulse structure claimed by the amateur astronomer on October 31st, 0.8-second pulses, separated by 3.2-second intervals. Not identical, but close enough to raise eyebrows. One astrophysicist, commenting anonymously on a SETI forum, put it this way: "If I saw that frequency in an artificial satellite, I'd assume it was a clock signal. If I saw it in a natural object, I'd be very confused." A clock signal. In electronics, a clock signal is a regular pulse used to synchronize components. Every computer has one. Every radio transmitter, every spacecraft. If the Juno disturbance was caused by something with an internal clock, something that was broadcasting or transmitting or simply operating, then it wasn't natural. But again, this is speculation. The data is real. The interpretation is uncertain. And NASA officially has said nothing. But unofficially there are rumors that the Juno team has been in contact with the team tracking 3I Atlas. That data is being shared, that simulations are being run, and that somewhere in a lab at JPL or MIT or ESA, someone is building a model of what a distributed probe network would look like, how it would behave, how we might detect it, not because they believe it's happening, but because they can't afford to assume it's not. On November 22, 2025, something strange happened on Mars. For 6 hours, all communication with the Martian surface went dark. Not completely. The orbiter's NASA's Mars Reconnaissance Orbiter, ESA's ExoMars Trace Gas Orbiter, and others continued transmitting data back to Earth without issue. But the surface assets, rovers, landers, instruments went silent. Curiosity stopped responding. Perseverance stopped responding. Even the seismometers left behind by the InSight lander, which had been transmitting passive data for years, went quiet. For 6 hours, Mars was a ghost world. The initial assumption was a technical glitch, perhaps a solar flare, though none had been detected. Perhaps a software bug, though the systems are designed with redundancy. Perhaps interference from some unknown source. But by the time contact was restored at 1847 UTC, the engineering teams were deeply concerned, because the blackout hadn't been uniform. Curiosity came back online first after 4 hours. Perseverance took 5, and the InSight seismometers didn't resume transmission until nearly 6 hours had elapsed. It was as if something had systematically shut them down, one by one, and then released them in sequence. But what? The first theory was electromagnetic interference. If a powerful burst of radio noise had swept across Mars, it might have temporarily overwhelmed the receivers on the surface assets, forcing them into safe mode. But the orbiters, which are much more sensitive, detected nothing. No bursts, no anomalies, just the usual background hum of the Martian ionosphere. The second theory was a software issue. Perhaps a scheduled update had gone wrong, causing the systems to reboot simultaneously. But the blackout had occurred at 12:47 UTC, not a scheduled maintenance window for any of the missions. The third theory was physical. Perhaps dust, perhaps a localized sandstorm. But the orbiter's cameras showed clear skies over both Curiosity and Perseverance. No dust, no storms. So what was it? On November 25th, ESA released a brief statement acknowledging the blackout and stating that all systems are now operating normally. They emphasized that no data had been lost and that the incident was under investigation. But they didn't explain what had happened, and they didn't mention 3I Atlas. But other people did. On November 26th, an astronomer at the University of Arizona posted a blog entry titled Mars 3I Atlas and the Geometry of Alignment. The entry was short, speculative, and carefully worded, but the core claim was striking. At the time of the Mars blackout, 3I Atlas was in near-perfect alignment with Mars as seen from Earth. Not perfectly aligned, not occulting the planet, but close, within a few degrees. And if 3I Atlas had released probes, if those probes were now distributed throughout the inner solar system, one of them might have passed near Mars around the time of the blackout. The blogger didn't claim this was what happened, but they posed the question: if you wanted to study Mars, its atmosphere, its surface, its electromagnetic environment, how would you do it without being detected? You'd wait until you were in a position where Earth's instruments couldn't distinguish your signal from the background. You'd position yourself along the line of sight between Mars and Earth, and then you'd broadcast, or scan, or probe, for just a few hours, just long enough to gather data, and then you'd vanish. The blog post gained traction quickly. Within 24 hours it had been shared thousands of times. Science journalists reached out for comment, and NASA, in response to mounting pressure, issued a second statement on November 28th. The temporary loss of communication with surface assets on Mars was due to a transient signal interference event of unknown origin. All systems have been thoroughly tested and are functioning as expected. There is no evidence linking this event to any external object. No evidence, but no explanation either, and the phrase of unknown origin lingered in the air like smoke. Because if NASA didn't know what caused the blackout, that meant one of two things. Either they were still investigating, or they had investigated and didn't like what they found. Either way, the silence felt deliberate. And when you combine the Mars blackout with the Juno anomaly, with the amateur signal claims, with the velocity discrepancies and the orbital capture and the asymmetric brightness and the radio quiet behavior and the aligned approach and the CO2 purity and the stable rotation, when you combine all of it, you're left with a picture that refuses to come into focus, a pattern that suggests intent but never proves it, an object that behaves like it knows we're watching but never confirms or denies, and a growing sense that maybe we're not the ones conducting the investigation, maybe we're the ones being investigated. By early December 2025, the speculation around 3I Atlas had reached a tipping point. Science forums were flooded with theories. Amateur astronomers were organizing coordinated observation campaigns. And, in a rare move, several prominent astrophysicists began speaking publicly about the object, not to endorse the more exotic hypotheses, but to push back against them. On December 3rd, an article appeared in Nature titled 3I Atlas and the Dangers of Premature Speculation. The article was signed by over 200 researchers, including several former NASA administrators and ESA mission scientists. The core argument was straightforward. Yes, 3I Atlas exhibits unusual characteristics, but unusual does not mean artificial. The history of astronomy is full of objects that initially appeared anomalous, but were later explained by natural processes. Pulsars, fast radio bursts, even Oumuamua. The article urged caution. It called for continued observation, rigorous analysis, and a commitment to following the data wherever it leads, but not jumping to conclusions in the absence of definitive evidence. It was a reasonable position, a scientific position, and it was completely ignored by the public, because by then 3I Atlas had become something more than an astronomical object. It had become a symbol, a Rorschach test, a blank screen onto which people projected their fears, their hopes, their beliefs about humanity's place in the universe. For some, the object represented proof that we are not alone, that somewhere out there intelligence exists, that contact, however indirect, is possible. For others, it represented a threat, an unknown force lurking at the edge of our solar system, watching, waiting, perhaps, preparing. And for a small but vocal minority, it represented a test, a challenge, an invitation to rise to the occasion and prove ourselves worthy of joining the cosmic community. None of these interpretations were scientific, but they were powerful. On December 10th, a second article appeared, this time in Science, titled The Signal-to-Noise Problem in Interstellar Object Studies. The article focused on the difficulty of distinguishing true anomalies from observational artifacts, instrumental errors and statistical flukes. The authors pointed out that 3I Atlas had been observed by dozens of telescopes using different techniques at different wavelengths, and in every case, the data quality was limited by distance, brightness, and resolution. The object was simply too far away, too dim, and too small to study in detail. Many of the reported anomalies, the velocity discrepancies, the spectral changes, the asymmetric brightness, could be artifacts of the observation process itself, not real features of the object, but illusions created by the limits of our instruments. The article concluded with a plea. We must resist the temptation to see patterns where none exist. The universe is strange enough without adding speculation to the mix. It was a fair point, but it didn't answer the central question. If the anomalies are just artifacts, why do they all point in the same direction? Why do they all suggest control? Why do they all hint at design? And why, if the object is natural, does it keep behaving in ways that challenge our understanding of what natural means? One researcher, speaking off the record to a journalist, put it more bluntly. Either we're seeing the most improbable series of coincidences in the history of astronomy, or we're seeing something we don't have a framework for yet, and I'm not sure which option is more unsettling. But the scientific establishment officially remained unmoved. On December 15th, NASA held a press conference, ostensibly to discuss the upcoming Artemis missions, but the first question from the press was about 3I Atlas. The NASA administrator, carefully composed, gave a measured response. 3I Atlas is a fascinating object. We are continuing to monitor it closely, but at this time, there is no evidence to suggest it is anything other than a natural interstellar comet. We encourage the public to focus on the science, not the speculation. A journalist followed up, but what about the orbital capture? What about the velocity anomalies? The administrator smiled. Comets are complex objects. We're still learning how they behave. Anomalies don't imply aliens. The press conference moved on, but the question lingered. Because if anomalies don't imply aliens, what would? What threshold of strangeness would need to be crossed before the scientific establishment took the possibility seriously? A radio signal? Physical contact? A message written in the sky? Or would even that be dismissed as a natural phenomenon we simply didn't understand yet? The truth is, science is conservative by design. It has to be. The burden of proof is high, and it should be. Extraordinary claims require extraordinary evidence, but there's a flip side to that conservatism: blindness. If you spend your entire career assuming the universe operates by certain rules, it's easy to miss the moment when those rules stop applying. It's easy to explain away every anomaly, to find a natural cause for every oddity, to dismiss every outlier as noise, and by the time you realize you were wrong, by the time the evidence becomes undeniable, it might already be too late. Not too late for science. Science will catch up eventually. It always does. But too late to respond. Too late to prepare. Too late to decide as a species what we want to do about the fact that we are not alone. On December 20th, 2025, Avi Loeb published an op-ed in the New York Times titled "The Case for Taking 3I Atlas Seriously." The piece was vintage Loeb, provocative, unapologetic, and deeply informed. He reviewed the evidence, he acknowledged the uncertainties, and then he made a simple argument. We should send a mission, not because we know 3I Atlas is artificial, but because we don't know that it isn't. If there's even a 1% chance that the object is a probe, a sensor, a piece of technology from beyond our world, then studying it should be humanity's top priority, because the knowledge we could gain, the confirmation that we are not alone, the insights into how other intelligences build, think, explore would be worth any cost. And if we're wrong, if we send a mission and discover it's just a comet, then we learn something about comets. We advance planetary science. We test new propulsion technologies. We lose nothing. But if we're right and we do nothing, then we will have missed the opportunity of a lifetime, of 1,000 lifetimes. The op-ed went viral. It was translated into dozens of languages. It was debated on television, in classrooms, in boardrooms, and for a brief moment, the world seemed to hold its breath, because for the first time in modern history, the possibility of contact, real, tangible, undeniable contact, felt within reach. Not someday, not in the distant future, now. But as of December 31st, 2025, no mission has been approved, no spacecraft has been built, no plan has been announced. 3I Atlas continues its slow drift outward, past Mars, toward the asteroid belt, receding from the Sun. And we continue to watch, to measure, to speculate, waiting for the next anomaly, the next clue, the next piece of evidence that might finally tip the scales. But what if the evidence never comes? What if the object simply fades from view, lost in the darkness of the outer solar system, leaving us with nothing but questions? Would that be proof of its natural origin, or proof of its discretion? In mid-December, a research team at Caltech published a technical paper that received almost no media attention, but among astronomers and SETI researchers, it was quietly revolutionary. The paper was titled Optimal Strategies for Long-Duration Surveillance of Planetary Systems by Autonomous Probes. It wasn't about 3I Atlas specifically. It was a theoretical study, exploring how an advanced civilization might design a network of self-sufficient observation platforms to monitor distant star systems over timescales of thousands or millions of years. The conclusion was elegant. You wouldn't use one large probe. You'd use many small ones. Each probe would be independent, capable of maneuvering, collecting data, and transmitting back to a central node or directly to the home civilization. They would be distributed throughout the target system, positioned at strategic points, near planets, near the star, near resource-rich asteroids or moons. They would be quiet, non-reflective, radio silent unless transmitting, and they would operate on timescales far exceeding human lifespans, patiently gathering information across centuries. The paper called this the distributed observer hypothesis, and while the authors never mentioned 3I Atlas by name, the implications were obvious. If the distributed observer hypothesis is correct, then what we're seeing isn't one object, it's one node. The mothership, the relay station, the anchor point for a network of smaller probes that we simply can't detect yet. Those probes could be anywhere. Near Earth, near Mars, in orbit, around Jupiter, drifting through the asteroid belt, each one silent, each one too small to resolve with our current instruments, each one watching. And if that's true, then 3I Atlas's orbital capture isn't the end of the story. It's the beginning, because a distributed network doesn't just observe, it adapts, it learns, it waits for the right moment to reveal itself or to act. The paper included several testable predictions. If the distributed observer hypothesis were real, we should see transient signals at unexpected locations, too brief to localize but consistent with probe-to-node communication, anomalous electromagnetic disturbances near planetary bodies, especially during periods of orbital alignment, patterns in the distribution of unexplained events, signal detections, spacecraft anomalies, communication blackouts that correlate with the positions of known interstellar objects. And when independent researchers began combing through archival data looking for those patterns, they found something. Not proof, but correlations. In 2017, shortly after Oumuamua passed through the inner solar system, there were 3 separate reports of brief, unexplained radio signals, one from the Arecibo Observatory, one from the Parkes Radio Telescope in Australia, and one from the Green Bank Telescope in West Virginia. All 3 were dismissed as interference at the time. In 2019, during 2I Borisov's flyby, the Mars Reconnaissance Orbiter experienced a minor telemetry glitch, a brief dropout in its data stream that lasted approximately 90 seconds. The incident was logged but never explained, and in 2021, the James Webb Space Telescope, while still undergoing calibration, detected a faint infrared source that appeared for less than 10 minutes and then vanished. The source was never identified. Individually, these events mean nothing. Glitches happen. Instruments malfunction. Interference is common. But when you plot them on a timeline, alongside the known trajectories of Oumuamua and 2I Borisov, a pattern emerges. Each event occurred when an interstellar object was within a few AU of a major planetary body. Coincidence? Probably. But the possibility, the slim, uncomfortable possibility, is that we've been under observation for years. That Oumuamua wasn't the first visitor, just the first one we noticed. That 2I Borisov wasn't alone. And that 3I Atlas is simply the latest and perhaps most deliberate entry in a catalogue of surveillance platforms. Seeded throughout our solar system, would we even recognize a machine intelligence? That's the question that haunts this entire investigation, because if an object is designed to look natural, to mimic the behavior of a comet or asteroid, to blend in with the background noise of the solar system, how would we distinguish it from the real thing? The answer is, we might not. Not unless it wants us to. And that brings us back to ambiguity, to the maddening, deliberate refusal of 3I Atlas to commit, to reveal itself or explain itself or do anything definitive. Maybe that's the point. Maybe the object is designed to hover on the edge of detection, just strange enough to notice but never strange enough to prove, a test of our observational capabilities, a measure of our technological readiness. Or maybe it's simpler than that. Maybe the object doesn't care whether we notice or not. Maybe it's here for its own reasons, executing a plan that has nothing to do with us, and we're just background. Data interesting perhaps, but ultimately irrelevant. Either way, the distributed observer hypothesis suggests something chilling. If 3i Atlas is part of a network, then it's not alone. And neither are we. One of the strangest aspects of the 3i Atlas story is how quiet the professional astronomical community has become. In the early weeks after discovery, there was excitement. Papers were published. Observations were shared. Data was debated openly. But by late December, the flow of information had slowed to a trickle. No new papers appeared on the Arkwactive server. No press releases from NASA or ESA. No interviews with mission scientists. Just silence. And when journalists reached out asking for updates, for clarifications, for comments on the latest amateur observations, the responses were polite but non-committal. We're still analyzing the data. Nothing conclusive yet. We'll issue a statement when we have something to report. But weeks passed, then months, and still no statement. Came why? One possibility is bureaucratic. Space agencies move slowly. Data analysis takes time. Peer review is a rigorous process, and no one wants to make a public claim that turns out to be wrong. But another possibility is more unsettling. What if the professionals have found something significant, but don't know how to talk about it yet? Think about it. If NASA or ESA had conclusive evidence that 3i Atlas was artificial, they couldn't just announce it. Not without preparation. Not without coordination across governments, across institutions, across the entire scientific establishment. Because such an announcement wouldn't just be scientific news. It would be historical. It would redefine humanity's understanding of its place in the universe. It would trigger political, social, economic consequences that no single agency could manage alone. So they'd wait. They'd verify. They'd bring in more experts. They'd run simulations, cross-check data, rule out every possible natural explanation. And in the meantime, they'd say nothing. This is speculation. There's no evidence of a cover-up, no whistleblowers, no leaked documents. But the silence is conspicuous. And it's made more conspicuous by the fact that several astronomers who were initially vocal about 3i Atlas have stopped speaking publicly. One researcher, who had been giving regular interviews in November, declined to comment in December, citing institutional constraints. Another deleted a blog post speculating about the object's trajectory. A third abruptly cancelled a scheduled conference talk on interstellar objects. None of this proves anything. People get busy, priorities shift, institutions impose communication guidelines, but taken together, it feels like a door closing, like a conversation ending before it reaches its conclusion. And that's frustrating, because the public ordinary people, not just scientists, have a right to know what's happening. If 3i Atlas is just a comet, fine. Tell us. Show us the data. Explain the anomalies. But if it's something more, if there's even a chance it's something more, then hiding behind institutional caution isn't just unscientific, it's irresponsible. Because the longer the silence lasts, the more room there is for speculation, for misinformation, for fear. And fear left unchecked can do more damage than the truth ever could. On January 12, 2026, a petition appeared on change.org calling for NASA to release all data related to 3i Atlas and to establish an independent review panel to evaluate the evidence for artificial origin. Within 48 hours, the petition had over 500,000 signatures. NASA did not respond. While the professionals retreated into silence, the amateurs grew louder. By January 2026, a loose network of backyard astronomers, radio enthusiasts, and citizen scientists had organized itself into what they called the 3i Atlas Observation Collective. They maintained a shared database of observations, a Discord server for real-time coordination, and a GitHub repository where anyone could upload data or analysis scripts. The collective had no funding, no institutional backing, just curiosity and an internet connection. But what they lacked in resources, they made up for in numbers. Over 300 people scattered across 6 continents, tracking the object every clear night, pooling their data, cross-referencing their findings. And in mid-January, they found something the professionals had missed, or at least, something the professionals hadn't publicly reported. One member of the collective, a retired engineer in New Zealand, had been monitoring the object's light curve. A light curve is just a graph of an object's brightness over time. For most asteroids and comets, light curves are irregular, fluctuating as the object tumbles and rotates. But 3I Atlas's light curve was different. It was almost perfectly smooth, too smooth. The rotation period remained stable at 11 hours. The brightness variations were minimal, less than 2% peak to peak. But on January 14th, something changed. For approximately 40 minutes, the object brightened by about 5%. Then it returned to baseline. The engineer double-checked his instruments. He cross-referenced his data with 2 other collective members in Australia and South Africa. All 3 confirmed the same event, a brief, symmetrical brightening, no corresponding change in rotation rate, no spectral shifts, just a pulse of light. The collective debated what it might mean. A flare? Outgassing? A surface feature rotating into view? But none of those explanations fit perfectly. And then, 2 days later, it happened again. Same duration, same magnitude, same symmetry. And this time, it was accompanied by something else. A faint radio signal, not from 3I Atlas itself, but from somewhere nearby. The signal was detected by an amateur radio astronomer in Arizona, a member of the collective who had been scanning the hydrogen line every night for weeks. The signal was brief, less than 5 seconds, and it was weak, but it was there. And it occurred at exactly the same time as the optical brightening. The collective compiled a report. They shared it publicly on their GitHub repository, and within hours it had been downloaded by thousands of people. A journalist from Wired picked it up and wrote an article. Amateurs detect coordinated signals from 3I Atlas. Is NASA listening? The article was speculative, but it was based on real data, data that anyone could verify. And for the first time since the discovery, the narrative began to shift. Because if the amateurs could detect something that the professionals either missed or chose not to report, what did that say about the state of the investigation? It said the professionals weren't the only ones watching anymore. It said that in the age of the internet, of open-source tools, of global collaboration, you didn't need $1 billion telescope to make a discovery. You just needed patience and attention, and maybe, just maybe, a willingness to look at the data without preconceptions. By late January 2026, 3I Atlas had transcended astronomy. It had become a cultural phenomenon. Books were written, documentaries were produced, podcasts dissected every detail, and on social media the object had become a symbol interpreted differently by different communities, but always with intensity. For some, it represented hope, proof that we are not alone. That, somewhere in the vast darkness, intelligence exists. That contact, however indirect, is imminent. For others, it represented danger, an unknown entity, lurking at the edge of our world, its intentions unknowable, a reminder that the universe is not benign. And for a smaller, quieter group, it represented something else, a mirror. Because the way we react to 3I Atlas, the way we interpret its ambiguity, the stories we tell about it, the fears and hopes we project onto it, reveals more about us than it does about the object. If we assume it's hostile, maybe that says something about our own history, our own violence. If we assume it's watching us, maybe that says something about our narcissism, our belief that we matter. And if we assume it's just a comet, if we cling to the simplest explanation, even as the anomalies pile up, maybe that says something about our fear of the unknown, our need for the universe to remain comprehensible. One artist, in February 2026, created an installation called The Observer Observed. It consisted of a single point of light in a darkened room, suspended at eye level. Visitors were invited to stand and watch the light, which pulsed irregularly for as long as they wanted. But hidden cameras recorded the visitors, and their images, hundreds of faces staring into the light, were projected onto the walls outside the installation. The message was clear. When we look outward, we also look inward. On February 14, 2026, a major Hollywood studio announced a film project based on 3I Atlas. The logline described it as a speculative thriller exploring humanity's first contact with an extraterrestrial intelligence. The announcement was met with mixed reactions. Some praised it as an opportunity to bring the story to a wider audience. Others criticized it as exploitative, turning real science into entertainment, blurring the line between fact and fiction. Avi Loeb, in an interview, offered a more measured take. Art and science have always informed each other. If a film inspires young people to study astronomy, to ask questions, to look up, then it's done something valuable, even if it takes liberties with the data. But not everyone was so sanguine, because the cultural response, the movies, the books, the memes, had an unintended consequence. It made 3I Atlas feel familiar, normal, safe. It domesticated the mystery. And in doing so, it risked inoculating the public against the real implications. Because if we treat the object as just another story, just another piece of content to consume and forget, we might miss the moment when the story becomes real. When the data shifts from suggestive to conclusive. When the probe, if that's what it is, reveals itself. And by then, it might be too late to respond thoughtfully. We'll have spent so much time speculating, so much energy debating, that when the answer finally arrives, we'll be exhausted, or worse, indifferent. That's the real danger. Not the object itself, but our reaction to it. On March 3, 2026, everything changed. At 0217 UTC, the Very Large Telescope in Chile captured an image of 3I Atlas that was different from every image taken before. The object was no longer alone. Approximately 1,200 kilometers from the main body, a second point of light appeared, faint, barely resolvable, but present. At first, the observation team thought it was a background star, a distant galaxy, an artifact of the imaging process. But over the next 6 hours, as the telescope continued tracking, the second point of light moved. It wasn't in the background, it was traveling alongside 3I Atlas, maintaining a consistent separation distance, a companion object. Within 24 hours, the observation had been confirmed by 2 other telescopes, Keck in Hawaii and the Hubble Space Telescope. The companion was real, and it was small. Estimates based on its brightness suggested a diameter of no more than 50 meters, roughly the size of a small building. It showed no sign of outgassing, no coma, no tail, just a cold, dark object drifting alongside the main body. But here's what made it extraordinary. The companion's trajectory didn't match the gravitational dynamics of a natural ejection. If 3I Atlas had shed material, if it had fragmented during perihelion, releasing debris, that debris should have followed a diverging path, gradually separating from the main body over time due to slight differences in velocity and gravitational perturbations. But the companion wasn't diverging. It was paralleling. It was staying close, as if it were tethered or controlled. On March 5th, a hastily convened press conference was held at ESA headquarters in Paris. The announcement was careful, measured, but unambiguous. We have detected a secondary object in proximity to 3I Atlas. The nature and origin of this object are currently under investigation. We urge the public to avoid speculation and to await further analysis. But the public didn't wait. Within hours, the news had spread across every platform. Social media exploded. News networks went live. And for the first time, mainstream outlets began treating the possibility of artificial origin not as fringe speculation, but as a legitimate hypothesis. Because if the companion was natural, why wasn't it drifting away? And if it was artificial, if it had been released deliberately, if it was maneuvering, if it was a probe, then 3I Atlas was no longer just an anomaly. It was confirmation. But confirmation of what exactly? That's the question that dominated the next few weeks. Because the companion didn't do anything. It didn't transmit. It didn't change course. It didn't approach Earth or any other planet. It just followed, silent, patient, like it was waiting. On March 10th, Scott Bolton, the principal investigator for the Juno mission, gave an interview to Science magazine. He was asked about the November 18th magnetometer anomaly and whether it might be related to the newly discovered companion object. His answer was cautious. There are patterns in the data that are difficult to explain with conventional models. We're exploring multiple hypotheses. The interviewer pressed, including the hypothesis that these are artificial objects? Bolton paused. We're not ruling anything out. It was the first time a senior NASA scientist had publicly acknowledged the possibility, and with that acknowledgement, the floodgates opened. On March 15, 2026, NASA announced an emergency mission. Proposal: Project Rendezvous. The goal was simple: send a spacecraft to intercept 3I Atlas and its companion, to study them up close, to gather data that ground-based observations simply couldn't provide. The mission would be fast-tracked. Normally, a planetary mission takes years to design, build, and launch, but Project Rendezvous was designed to launch within 6 months, an unprecedented timeline. The spacecraft would be small, stripped down, essentially a camera, a spectrometer, and a radio. Transmitter, attached to a propulsion module capable of matching 3I Atlas's trajectory. If successful, it would reach the object by late 2027. The announcement was met with both enthusiasm and criticism. Enthusiasts praised it as bold, necessary, visionary. Finally, they said, we're taking the possibility seriously. Finally, we're acting instead of just watching. Critics called it reckless, a waste of resources, a capitulation to hysteria. One astronomer described it as the most expensive response to a comet in history. But the criticism missed the point. Because Project Rendezvous wasn't about confirming or denying the artificial origin hypothesis, it was about gathering data, real, close-up data that would allow us to make an informed decision instead of endlessly speculating. And there was a deeper reason, too, one that wasn't stated in the official press release, but was understood by everyone involved. If 3I Atlas is artificial, and we do nothing, then history will judge us. As the generation that saw evidence of extraterrestrial intelligence and looked away, we couldn't afford that. Not morally, not historically. The mission was green-lit. But as engineers began designing the spacecraft, a question emerged. What if the object doesn't want to be approached? What if getting close triggers a response? No one had an answer. In mid-April 2026, as Project Rendezvous was being assembled, astronomers tracking 3I Atlas noticed something new. The object's trajectory had changed again, not dramatically, but measurably. Over the previous month, 3I Atlas had been drifting outward, as expected, following its elliptical orbit away from the Sun. But the latest observations showed a slight deviation, a small but persistent lateral shift, perpendicular to the expected path. It was as if the object were being nudged sideways. The first explanation, gravitational perturbations from Jupiter or Saturn, was quickly ruled out. The effect was too large, occurring too quickly. The second explanation, outgassing, remained implausible. No coma, no jets, no thermal signature. That left one option: active maneuvering. By late April, the trajectory shift had accumulated into a displacement of nearly 100,000 kilometers from the predicted position. That's enormous. It's not something that happens accidentally. And the direction of the shift was striking. The object was moving toward the plane of the ecliptic, toward the region of space where the planets orbit, not toward Earth specifically, but toward the general vicinity of the inner solar system. One astronomer, in a private email that was later leaked, described it as closing the distance. On April 28th, NASA held another press conference. This time the tone was different, more serious, less equivocal. We have observed trajectory changes in 3I Atlas that cannot be explained by known natural forces. We are continuing to monitor the situation closely. A journalist asked the obvious question, "Are you saying the object is under intelligent control?" The NASA administrator took a breath. "We are saying the data is anomalous, and we are taking it seriously." It wasn't confirmation, but it was close. On May 1st, 2026, the SETI Institute launched the largest coordinated radio observation campaign in history. The goal: listen to 3I Atlas and its companion at every wavelength, every hour of every day, for 3 months. Over 50 radio telescopes participated, from the Arecibo Observatory to the RTU square-kilometre array in South Africa, from amateur setups in garages to billion-dollar facilities, the entire global network turned its attention toward the object. They called it the Great Listening. The campaign was unprecedented in scope, and it was driven by a single urgent question. If the object is artificial, is it communicating? For the first 3 weeks they heard nothing, just the usual cosmic background, the hiss of distant galaxies, the crackle of pulsars, but nothing from 3i Atlas. And then on May 22nd at 14:03 UTC something appeared. It wasn't a signal, not in the traditional sense. It was a pattern, a subtle modulation in the radio noise around 1420 MHz, the hydrogen line. The modulation lasted for approximately 90 seconds, cycling through a series of amplitude variations that seemed almost rhythmic. But here's what made it extraordinary. The pattern repeated. 12 hours later, at 02:03 UTC on May 23rd, the same pattern appeared again. Same frequency, same duration, same structure. And then again, 12 hours after that. It wasn't continuous, it wasn't a beacon, but it was regular, and regularity implies structure. Structure implies intent. By May 30th, the pattern had been detected 16 times, always at 12-hour intervals, always at the hydrogen line. The SETI team analyzed the pattern exhaustively. They searched for mathematical sequences, for prime numbers, for encoded information. They found nothing definitive. But the pattern itself, the mere fact of its regularity, was enough, because natural phenomena don't repeat on a 12-hour cycle unless they're driven by rotation, and 3i Atlas's rotation period was 11 hours, not 12. So what was causing the pattern? One possibility: the companion object. If it were orbiting 3i Atlas and if it were emitting something, heat, radio waves, particles, then that emission might appear periodic from Earth's perspective as the companion moved in and out of view. But if that were true, the period should match the orbital dynamics, and preliminary calculations suggested an orbital period of roughly 12 hours. It fit. The companion was orbiting the main body, and it was transmitting. Not to us, not deliberately, but transmitting nonetheless, perhaps as a byproduct of its operation, perhaps as internal communication, perhaps as a navigational beacon. We don't know. But the regularity was undeniable, and for the first time, the scientific community began to coalesce around a consensus. 3i Atlas was not a comet. By June 2026, the story of 3i Atlas had become the defining issue of the year. Governments convened emergency sessions. The United Nations established a special committee on extraterrestrial contact. And in a rare show of unity, the world's major space agencies, NASA, ESA, Roscosmos, CNSA, ISRO, issued a joint statement. We are witnessing an event of profound historical significance. Regardless of the ultimate nature of 3i Atlas, its study represents an opportunity to advance our understanding of the universe and our place within it. We call for international cooperation, transparency, and a commitment to following the evidence wherever it leads. It was a carefully worded statement. It didn't claim the object was artificial, but it didn't dismiss the possibility either. And for many that was enough, because after months of ambiguity, of speculation, of conflicting data, the simple act of acknowledging the stakes of taking the possibility seriously felt like progress. But not everyone was satisfied. On June 10th, a coalition of scientists and activists published an open letter demanding immediate transparency. They called for the release of all data related to 3i Atlas, the establishment of independent review panels, and public hearings on the implications of potential contact. The letter was signed by over 10,000 people, including 3 Nobel laureates. Within a week, NASA announced that all Project Rendezvous data would be made publicly available in real time once the mission launched. It was an unprecedented move, and it signaled a shift. The age of secrecy was over. From now on, whatever we learned about 3i Atlas, the world would learn together. But with transparency came risk. Because if the object revealed itself, if it transmitted a message, if it changed course toward Earth, if it did anything unambiguous, there would be no time for governments to deliberate, for experts to consult, for institutions to prepare. The response would be immediate, chaotic, global, and no one knew if we were ready for that. On July 8, 2026, the Hubble Space Telescope detected a third object, another companion. Smaller than the first, fainter, but undeniably there. It was located approximately 2,400 kilometers from 3I Atlas, on the opposite side from the first companion. And like the first, it wasn't drifting. It was holding position. The discovery sent shockwaves through the astronomical community. Because one companion could be explained barely as a fragment, a piece of debris, something ejected during perihelion. But two companions, symmetrically positioned, maintaining stable separations. That couldn't be natural. On July 10th, ESA released a statement. We have confirmed the presence of a second companion object near 3I Atlas. Analysis is ongoing. That was all they said, but it was enough, because the geometry was unmistakable. The two companions were positioned like sentinels, like guards, or sensors, and if there were two, might there be more? Over the next week, telescopes around the world conducted intensive observations, searching for additional objects. They found one more, a fourth object, even smaller, located roughly 3,000 kilometers from the main body, completing what appeared to be a triangular configuration. 3 companions, arrayed in a pattern, not random, not chaotic, deliberate. By mid-July, the consensus had shifted irreversibly. 3I Atlas was not a natural object. It was a construct, a system, a network of components working in coordination. And it was here, in our solar system, watching. With the discovery of multiple companions, the conversation changed. It was no longer about whether 3I Atlas was artificial. It was about what that meant. Philosophers, ethicists, theologians' voices that had been largely absent from the debate now entered the discourse. One philosopher wrote, "The confirmation of extraterrestrial intelligence is not just a scientific milestone, it's an existential one. It forces us to reconsider fundamental questions. What is intelligence? What is life? What are we?" Another posed a darker question. If we are being observed, what does that make us? Subjects? Specimens? Exhibits? The debate fractured along familiar lines. Optimists argued that contact, even indirect contact, represented an opportunity, a chance to learn, to grow, to join a larger cosmic community. Pessimists warned of naivety, of assuming benevolence where none might exist, of forgetting that history, even on Earth, is full of examples where contact between unequal civilizations ended badly for the less advanced. And a third group, smaller, quieter, suggested that maybe the question wasn't about them at all. Maybe it was about us, because the way we react to 3I Atlas reveals who we are, our fears, our hopes, our capacity for wonder or paranoia. If we respond with curiosity, with openness, with a willingness to learn, then maybe, just maybe, we prove ourselves worthy of contact. But if we respond with fear, with aggression, with suspicion, then maybe we confirm every reason an advanced civilization might have for keeping its distance. One writer framed it this way: we are not being tested by the object, we are being tested by ourselves. It was a poignant thought, but it didn't answer the practical question: what do we do? Do we approach? Do we communicate? Do we wait? Project Rendezvous was still on schedule. The spacecraft was nearly complete, and barring unforeseen delays, it would launch in September. But now the mission carried a new weight, because it wasn't just about gathering data anymore. It was about making a statement, about declaring as a species that we are here, that we are aware, that we are ready or at least willing to engage with whatever lies beyond. And once that statement is made, it can't be taken back. On September 12, 2026, Project Rendezvous launched from Cape Canaveral. The spacecraft was small, barely 3 meters across, but it carried the hopes and fears of the entire world. The mission profile was straightforward: accelerate outward, match 3I Atlas's trajectory, approach to within 100 kilometers, and transmit high-resolution images and spectroscopic data back to Earth. If all went according to plan, the spacecraft would reach 3I Atlas by December 2027. 15 months. 15 months to wait, to wonder, to prepare. The launch was broadcast live. Over 1 billion people watched. And when the rocket lifted off, when the engines roared and the spacecraft climbed into the sky, there was a collective sense of something shifting. Not just the spacecraft, but humanity itself. Because for the first time in history, we were actively pursuing contact, not passively listening, not waiting for a signal. We were reaching out. And whatever came next, whether it was confirmation, revelation, or silence, we would face it together. The months following the launch were strange. On one hand, life continued. People went to work, governments functioned, markets operated. But underneath there was a tension, a low hum of anticipation, because everyone knew that sometime in late 2027, the spacecraft would arrive, and whatever it found would change everything. Scientists continued monitoring 3I Atlas. The object remained stable, drifting outward, the companions holding their positions. The 12-hour radio pattern continued, regular, unchanging, and the world waited. In October 2026, a survey asked people around the world a simple question. If 3I Atlas is confirmed to be artificial, how do you feel? The responses were split almost evenly. 34% said hopeful, 31% said afraid, 35% said uncertain. It was a reflection of the ambiguity, the not knowing, because the object hadn't done anything hostile, but it hadn't done anything reassuring either. It was just there, watching, waiting, like us. On December 18, 2027, the Project Rendezvous spacecraft reached 3I Atlas. At 0814 UTC, the first close-up images were transmitted back to Earth, and they were extraordinary. The main body of 3I Atlas was not a comet. It was a structure, angular, geometric, covered in what appeared to be panels, some reflective, others dark and matte. There were no craters, no signs of impact, no natural weathering. It looked built. The companions were equally striking, small, symmetrical, clearly manufactured. And on the surface of the main body, near one of the reflective panels, there was something else. A marking, a pattern, not random, not erosion, but deliberate. A symbol. The images were released publicly within hours, and the world saw for the first time undeniable evidence. We are not alone. In the weeks following the arrival, the data poured in. Detailed images, spectroscopic analyses, measurements of the object's composition, structure, thermal properties. Everything confirmed what the images had shown. 3I Atlas was artificial. But here's what the data didn't reveal. Who built it? Where it came from? Why it's here? The symbol on the surface remained undeciphered. The 12-hour radio pattern continued, but no message was detected. The object didn't respond to our presence. It didn't acknowledge the spacecraft. It just continued its slow drift outward, silent and inscrutable. And so, even with confirmation, the mystery remains. Because knowing that something is artificial doesn't tell you what it wants, or whether it even has wants. Maybe it's a probe. Maybe it's a monument. Maybe it's a warning. Or maybe it's something we don't have a word for yet. On February 14, 2028, Avi Loeb gave a final interview. He was asked, "Now that we know 3I Atlas is artificial, what's the next question?" He smiled. "The next question is the same as the first. Are we ready? Ready for what? For whatever comes next. Because 3I Atlas is not the end of the story. It's the beginning." And he was right. Because the object is still here, still in orbit, still watching. And now we watch back. If we are being observed, what do they see? A species capable of curiosity, of science, of reaching beyond itself, or a species still learning, still growing, still trying to understand its place in the vastness of space? Either way, the question remains open. And maybe that's the point. Maybe the answer isn't given. Maybe it's earned by how we respond, by what we do next, by whether we rise to meet the mystery or turn away from it. The sky is full of questions now, and somewhere in the cold dark between worlds something is watching, waiting to see what we become.